Hi, AP Chem. Okay, so we're going to discuss barometers very briefly. And the main question we're going to discuss is why barometers are made of mercury and not water. I mean, think about it. Water's not poisonous. They've suddenly decided mercury is poisonous. Why are barometers not made of water? Because you are going to use a water barometer when we do a lab in this chapter, and you are going to have to make some mathematical corrections for using the water barometer. Alright, here's a typical picture of a barometer. This is attributed to Torricelli. That's why he gets those units thrown at him. That's 760 Torricelli, Tor. So this is a real basic one from way back. They're a lot fancier nowadays. This is a bowl of mercury. Liquid at room temperature, used to be in thermometers, was a blast to play with. They don't put it into thermometers anymore because they found out it's poisonous. This is a column of mercury. This is elemental mercury. And this is exactly what it says, a vacuum. There's not one single particle of air in that vacuum. That is exactly what a vacuum is. Devoid of anything, nothing in there. If you were to shrink down in size and swim up that column to the vacuum, you would die because there's nothing to breathe. There's no oxygen particles, water particles, nothing above that mercury column. What typically happens is air pressure, and you've heard barometers if you've ever watched a weather report, the air pressure will push down on the bowl of mercury, causing the column to go up, and they literally measure the column of mercury. The higher the column, the higher the air pressure. If the air pressure is low, then the bowl of mercury rises slightly and the column actually lowers. So when the air pressure is low, so's the column. How do barometers work? Well, pressure is equal to force divided by a unit of area. Force is mass times gravitational pull, so that's basically gravity. And you use gravity a lot in physics, not so much in chemistry. And mass, of course, is the density times volume. Remember that density is a ratio of mass to volume. Well, mass is density times volume. So we're going to do a little substituting in, and we get pressure being equal to density times volume times gravitational pull divided by the area. For a column, volume is equal to height times area. So you substitute that in and you get a very simplistic calculation for pressure. Density times height times gravitational constant. Air pressure increases, mercury in column goes up. air pressure decreases, mercury in column goes down, which we just discussed at great length. A barometer is a device that measures atmospheric pressure. This is the one you always hear if you ever watch a weather report and they say, oh, barometric pressure over the East Coast is da-da-da-da-da, and they're going to get a storm. So the big question is, why mercury? Why not water? Water is very abundant. Why isn't water used? Two reasons. Reason number one, mercury is way more dense. The density of mercury is 13.6 grams per milliliter. And the density of water is 1.00 grams per milliliter. Now think about this logically. You can fit 13.6 grams into 1 milliliter as opposed to only 1 gram. So the water would require an awful large area because you can only get 1 gram in every 1 milliliter. Density plays an important role because you can fit more into a smaller area with mercury. Second reason, evaporation. Mercury's evaporation is very low. Keep in mind that's important because in that mercury column, you need this to be a vacuum. In order for this to be a vacuum, you can't have anything evaporating into it. With mercury, this remains basically a vacuum. With water, you suddenly have water molecules above, and it's no longer a vacuum. Now you have to take into consideration the pressure of those gas particles pushing down on the water. So this is water. And this is your mercury. So that's why mercury's a better pick. It stays a vacuum? Doesn't. You can get more into this area than this guy. So two very important reasons why water is not used like mercury. Alright, so column pressure is going to be pressure is equal to dGH. D is density, G is gravitational constant, H is the height in millimeters. I mean 760 millimeters of mercury. It is literally the height of the mercury column in millimeters. What we're going to do is we're going to do a little algebra, mathematical manipulation. We're going to figure out what it would take for a column to exert the same pressure as Mercury. Right, so what we're basically doing here is we are calculating a correction, let's call it a correction factor. To, let's see, to use, what do you want to call it? A correction factor to use for water to mercury. How's that sound? Alright, so here's what I'm going to do. I'm going to do algebra. In order for the pressure of mercury to be equal to the pressure of water, and I'm going to do a little algebra, the density of mercury times gravitational force, the height of the mercury column to be equal to the density of the water, gravitational force, and the height of the water column. Now, of course, we can use only one of these as constant for both mercury and water. So the G's are going to cancel out. And you have that the density of the mercury times the height of the mercury will be equal to the density of the water times the height of the water. Now we're dealing with the water, so I'm going to algebraically swing this around a little bit, and the density of the mercury Alright, so the height of the water will be some number multiplied by the height of the mercury in order to make a correction for it. Now plug in our values for density. And I get 13.6 grams per milliliter over 1.00 grams per milliliter. Those are the densities for mercury and water, respectively. Multiplied by the height of the mercury column will make a correction for the height of the water column. And what you get two things really. 13.6 multiplied by the height of the mercury column will be the equivalent to the height of the water, or the water column height divided by 13.6 will be the equivalent of the mercury. So these two things are basically a correction factor. What this means right here, basically speaking, is the height of any water column will be 13.6 times higher than mercury, than a mercury column. A column of water will be 13.6 times higher than a column of mercury to exert the same pressure. So this is your mercury column. So my water column would have to be 34 feet tall in order to exert the same pressure. There you go. Barometers.